All right, it looks like we're live. Previews up. I'm getting all sorts of push notifications. Okay, everything is looking good. Good morning, everybody. It's been a week since I last streamed, and that's because I had some emergency stuff to take care of back in another state. But I am done with that. I'm happy to report that everything seems to have been okay. So because of that, I'm able to continue on. And a few things changed since the last time I was streaming. Rust version 2018 came out. So last night I went ahead and Rust upped to a new version of the 2018 version, and I noticed that they also released the 2018 edition of the book, which looks like it's been forked from version 2. And it's just going to continue on. So I think that's where we're just gonna start using this from now on, and the 2018 version. So we were on chapter 19 in unsafe Rust, and specifically we were at using extern functions to call external code. Let's go find that section. Here we go. Let's also make this just a little bit bigger. Perfect. And is there anything else that I need to do to get set up? I don't think so. I'm gonna set up chat on my phone really quickly, just in case. I have noticed that this chat window sometimes doesn't load properly, which is fun. So if you do end up saying hi and I see it over here, then I can close my phone down. But with that, let's go ahead and get started and continue on with using extern functions to call external code. Sometimes your Rust code might need to interact with code written in another language. For this, Rust has a keyword, extern. Isn't that what we use for pulling in crates too? Good morning, Stacking. Sounds like you just missed story time. Oh, it was just the introduction to everything. It wasn't that big of a deal. But I'm glad you're here. Good morning. Welcome to the stream. Rust has a keyword extern that facilitates the creation and use of a foreign function interface, FFI. And FFI is a way for a programming language to define functions and enable a different foreign programming languages to call those functions. Listing 19.8 demonstrates how to set up an integration with the ABS function from the C standard library. Functions declared within extern blocks are always unsafe to call from Rust code. The reason is that other languages don't enforce Rust rules and guarantees, and Rust cannot check them, so responsibility falls on a programmer to ensure safety. So extern, just C. Function. So we define the function that we're going to use. But like, so we're telling it what function we are going to use, but obviously it's defined in C. And then in function main, we have our unsafe block, print line absolute value of -3 according to C. That actually seems pretty cool. Let's give that a shot in here. So we would want to extern. So they do have extern crate here, but instead of extern crate name, we're going to do extern C like that. And okay, so then immediately we have a block right there, and put in what functions we're going to use. So function ABS that takes in a I guess like a I32. What I32? And then it's gonna return and I32, and that's kind of it. We're just defining what the function is gonna be. And then in main, we're gonna use it in unsafe. Do we need a semicolon here? No. Foreign function is never used, ABS. Okay. So inside of here, we can now do print line. I guess it's gonna be unsafe. And then we'll just do print line, and we'll say ABS of -3 according to C. And it's going to be ABS -3. All right, well, it's not complaining to me, so that's a good sign. Cargo run, see if we get the ABS. ABS at -3 according to C3. So that actually worked. I do have node dash. So I have node 10.4.1 installed right now. I wonder if it's also easy for me to do, what function would I want to run in there? Extern. I wonder if it would recognize what this is and if it would work properly. Invalid ABI, expected one of. Oh, so look, and I guess ABS is part of some Linux standard library. Yeah, ABS, I've done C a long time ago, and ABS is one of the standard library calls. Looks like these are all of the external codes that we can call here. So I can't just do the name of a programming language and it'll find it in like the path or something. It has to be one of these. But C is one of those. But that would just be for the standard library. So maybe later we'll find out how to like run, like put, like let's say we create our own function in C. We want to run that. Someone posted a cool blog post the other day about using splice in Linux, which speed up grep by like 100 times. Wow, that's pretty cool. Are you talking about like how ripgrep is using, like is that using it, or is it something else? Or is it just C, like just using C splice? Within the extern C block, we list the names and signatures of external functions from another language we want to call. The C part defines which application binary interface the external function uses. The ABI defines how to call the function at the assembly level. The C ABI is the most common and follows the C programming language's ABI. It's something else. It's using C to call. Okay, so yeah, C can be pretty fast. Calling REST functions from other languages. We can also use extern to create an interface that allows other languages to call REST functions. Instead of an extern block, we add the extern keyword and specify the ABI to use just before the function keyword. We also need to add a #no-mangle annotation to tell the REST compiler not to mangle the name of this function. Mangling is when a compiler changes the names we've given a function to a different name that contains more information for other parts of the compilation process to consume, but is less human readable. Every programming computer languages mangles names slightly differently, so for a REST function to be nameable by other languages, we must disable the REST compiler's name mangling. In the following example, we make the call from C function accessible from C code after it's compiled to a shared library and linked from C. So no mangle pub extern C. So we're just making it available to C, function call from C, and then it's like this is what we're gonna do. That's actually pretty cool too. But I'm feeling like less. I'm not. if I can run this from like Node.js, then this adds a lot of really cool things that I can do with JavaScript servers using like Express and Node. I could ship off all of the really expensive calls over to Rust and have them do that. It's more about splices pretty fast. It allows you to copy memory from one file to another without hitting user space. That's actually pretty cool. Also isn't in place, so it's not actually like even copying memory. It's just doing it in the same piece of memory. That's where like remembering how like splice actually works is kind of no longer existent in my head. Accessing or modifying a mutable static variable. Until now, we've not talked about global variables, which Rust does support but can be problematic with Rust's ownership rules. If two threads are accessing the same mutable global variable, it can cause a data race. In Rust, global variables are called static variables. Listing 19.9 shows an example declaration and use of a static variable with a string slice as a value. So static hello world string slice equals hello world function main. So yeah, I mean we can just do that. Static variables are similar to constants, which we discussed in the differences between variables and constants section in chapter 3. The names of static variables are in screaming snake case. Okay, screaming snake by convention, and we must annotate the variable's type with, right, because this lists sort of lifetime. The ampersand single quote static stir. In this example, static variables can only store references with the static lifetime, which means the Rust compiler can figure out the lifetime. We don't need to annotate it explicitly. Accessing an immutable static variable is safe. If I remember correctly, it actually copies this into the source code, which is the reason why it's like always available. Constants and immutable static variables might seem similar, but a subtle difference is that the values in the static variable have a fixed address in memory. Using the value will always access the same data. Constants, on the other hand, are allowed to duplicate their data whenever they're used. Another difference between constants and static variables is that the static variables can be mutable. Really? Accessing and modifying mutable static variables is unsafe. Okay, that makes a lot more sense. Listing 19.10 shows how to declare, access, and modify a mutable static variable named counter. Yeah, because like normally if I'm making like a static, I'm thinking of it as a true constant in like a literal constant. I'm writing in there like the version number, something like a URL or something else that I always want the program to be going to. And if I want to update it, I want to pull up the source code and re-release. Static mute counter, so function add account. So yeah, it's mutable. Increment u32, so unsafe counter plus increment. So yeah, notice we can increment this outside of here. But this means that if we ever want to access it just to read it, it won't let us do that either. So we can try this too. So let's try down here. We'll do static mute. We basically do all uppercase to let us developers know that we're using static here. Equals 0. Do we have to give it type annotations too? Expected, yeah, so I do. So this is going to be a U2. Okay, so then I want to call update counter. and we're going to pass in just by 1. And then we want to print line counter now is counter. Now, of course, this won't work because I don't have this function, so let's create update counter. So I'm purposely not using the unsafe because I want to see what the compiler is, like how it yells at me. So function update counter. This is going to take a so increase by u32. This is not going to return anything because it's just going to update this counter. So we're just going to say counter plus equals increase by that. That's all we're going to need here. So you are being yelled at. Cannot find counter in this scope. Not found in this scope. That's really interesting. I wonder if we're going to get better error message. Nope, that's not right. Needs to be a ref to counter. Is that? So add to count. So what's interesting here is that in add to count, it's just taking the increment by here, but it's not like taking in counter, it just has access to it. I wonder if it's because this is defined above main and I defined it below. That doesn't seem to be. And I was hoping that it would tell me. That like something more about that. Right now it's just saying cannot find counter in a scope. Static mute counter type u32 equals this. Oh, you know what? It needs to be. I need to set this up here at the top. So we have extern C, we have use standard slice, and maybe right here I'll create static mute. That fixes this. Okay, so then here, use a mutable static requires unsafe function or block. So I can now safe. So that should make that happy. And then here it's the exact same thing. We need unsafe. And now if I run this, the counter is now 1. So that works for us. And it's the counter initially is set statically inside the source code. I mean, sorry, of course it's inside the source code, inside the binary that's created for us. I'm guessing unsafe in this case automatically takes the reference. I think that it's more interesting than that. So because we declare the counter up here, it's in the global scope. So it's just everywhere. So this function can access it because it is everywhere. Also, we have to use static to make sure that it's like actually stored as a as a literal u32 inside of the binary that's created. But we need to use unsafe because we're mutating it, and then we're reading it, and it's like unsure of what order that we're doing this in. I bet like we can get weird results if we do this with reds. Yeah, like we haven't used globals at all until now, and I'm pretty happy to continue not using them, really. As with regular variables, we specify mutability using the mute keyword. Any code that reads or writes from counter must be within an unsafe block. This code compiles and prints counter 3, as we would expect because it's single-threaded. Having multiple threads access counter would likely result in data races. With mutable data that's globally accessible, it's difficult to ensure there are no data races, which is why Rust considers mutable static variables to be unsafe. Where possible, it's preferable to use the concurrency techniques and thread-safe smart pointers we discussed in chapter 16. So the compiler checks that data access from different threads is done safely. More like you should just never use global. Yeah, I mean, that's kind of what I've just like over the years switched to. It's kind of like funny because when I first started programming, global seemed like the answer to everything. Didn't know how to, like, things were getting undefined or null or errors. Oh, just switch that to global and suddenly it's like all your code works. And now it's the opposite. I'm just seeing a spider crawling on the floor next to me, but it's decently far enough away from me that I'm okay with that. When to use unsafe code. Using, implementing an unsafe trait. The final action that works only with unsafe is implementing an unsafe trait. A trait is unsafe when at least one of its methods has some invariant that the compiler cannot verify. We can declare that a trait is unsafe by adding the unsafe keyword before trait and marking the implementation of the trait as unsafe too, as shown in listing 1911. So unsafe trait foo method goes here. I think we've, a trait. So basically make sure that we're going to have a method that's unsafe implementation foo for i32, and then we actually implement that method. Perfect. By using unsafe implement, we're promising that we'll uphold the invariants the compiler can't verify. As an example, recall the sync and send marker traits we discussed in the extensible concurrency with the sync and send traits section in chapter 16. The compiler implements these traits automatically if our types are composed entirely of send and sync types. If we implement a type that contains a type that is not send or sync, such as raw pointers, and we want to mark that type as send or sync, we must use unsafe. Rust cannot verify that a type upholds the guarantees that it can be safely sent across threads or accessed from multiple threads. Therefore, we need to do those checks manually and indicate as such with unsafe. When to use unsafe code. Using unsafe to take one of the 4 actions, or superpowers, just discussed isn't wrong, or even frowned upon. Well, I mean, okay, just to take one of the 4 actions. But it is trickier to get unsafe code correct because the compiler can't help uphold memory safety. When you have a reason to use unsafe code, you can do so, and having the explicit unsafe annotation makes it easier to track down the source of problems if they occur. And that's the end of this section. We are going to continue on to chapter 19.2, Advanced Lifetimes. In chapter 10, in the validating references with the lifetime section, you learned how to annotate references with lifetime parameters to tell Rust how lifetimes of different references relate. You saw how every reference has a lifetime, but most of the time, Rust will let you elide lifetimes. I'm actually not familiar with that word, elide. Elide definition. Emit a sound or syllable when speaking. Join together or merge. Okay. The first one didn't make sense. I think the spider went into the closet. I mean, that would be better than crawling up my legs, so. Okay. So I'm guessing like join lifetimes. Now we'll look at 3 advanced features of lifetimes that we haven't covered yet. Lifetime subtyping ensures that one lifetime outlives another lifetime. Lifetime bounds specifies a lifetime for a reference to a generic type. Inference of trait object lifetimes allows the compiler to infer trait object lifetimes and when they need to be specified. Ensuring one lifetime outlives another with lifetime subtyping. Lifetime subtyping specifies that one lifetime should outlive another lifetime. To explore lifetime subtyping, imagine we want to write a parser. We'll use a structure called context that holds a reference to the string we're parsing. We'll write a parser that will parse the string and return success or failure. The parser will need to borrow the context to do the parsing. Listing 1912 implements this parser code, except the code doesn't have the required lifetime annotations, so it won't compile. So we have struct context, which is just a string slice. Struct parser. Is this a tuple struct? That's really interesting. Struct parser, which is the standard like object syntax, context, and then a reference to context. Implement onParser, function parse, takes in reference to self, and returns a result with either nothing or an error, which is the string slice, and then we just return error. So reference to self dot context 0. So it is a tuple. I press a button on my mouse. Dot 0 and then 1 dot dot. So everything besides the first character we want to copy, like get a string slice and return that. Compiling the code results in errors because Rust expects lifetime parameters on the string slice in context and the reference to a context in parser. For simplicity's sake, the parse function returns result, a result type. That is, the function will do nothing on success, and on failure will return the part of the string slice that didn't parse correctly. A real implementation would provide more error information and would return a structured data type when parsing succeeds. We won't be discussing those details because they aren't relevant to the lifetimes part of this example. To keep this code simple, we won't write any parsing logic. However, it's very likely that somewhere in a parsing logic we would handle invalid input by returning an error that references the part of the input that's invalid. This reference is what makes the code example interesting in regard to lifetimes. Let's pretend that the logic of our parser is that the input is invalid after the first byte. Note that this code might panic if the first byte is not on a valid character boundary. Again, we're simplifying the example to focus on the lifetimes involved. To get this code to compile, we will need to fill in the lifetime parameters for the string slice in context and the reference to the context in parser. The most straightforward way to do this is to use the same lifetime name everywhere, as shown in listing 19.3. Recall from the lifetime annotations in struct definition section in chapter 10 that each of the struct context, so lifetime A, struct parser lifetime A, and implement lifetime A, is declaring a new lifetime parameter. While their names happen to all be the same, the 3 lifetime parameters declared in this example are not related. Yeah, I mean, so we know that. So struct context lifetime A. Okay, so this is all making sense in what we've seen before. This code compiles just fine. It tells Rust that a parser holds a reference to a context with lifetime A, and that context holds a string slice that can also live as long as the reference to the context in the parser. Rust compiler error message stated that lifetime parameters were required for these references, and we've now added lifetime parameters. Next, in listing 1914, we'll add a function that takes an instance of context, uses a parser to parse that context, and returns what parse returns. This code doesn't quite work. So function parsecontext so parsecontext takes in a context, and it's going to return the standard result, nothing in air, the string slice. So it's just going to return the struct parser context reference to context dot parse. Yeah, we're going to need lifetimes here too. We get two verbose errors when we try to compile the code with the addition of the parse context function. So parser does not live long enough, and context does not live long enough. Borrowed value must be valid for the anonymous lifetime number 1 defined for here. Interesting. These errors state that the parser instance that is created in a context parameter live only until the end of parse context function, but they both need to live for the entire lifetime of the function. In other words, parser and context need to outlive the entire function and be valid before the function starts, as well as after it ends, for all the references in the code to always be valid. The parser we're creating and a context parameter go out of scope at the end of the function because parse context takes ownership of the context. To figure out why these errors occur, let's look at the definitions in listing 1913 again, specifically the references in the signature of the parse method. The function parse, self, result, so that's the first time. Remember the elision rules? If we annotate the lifetimes of the references rather than eliding, the signature would be as follows. So function parse, lifetime A for self, result, lifetime A for string. That is, the error part of the return value of parse has a lifetime that is tied to the lifetime of parser, of the parser instance, that of self in a parse method's signature. That makes sense. The return string slice references the string slice in the constants instance held by the parser, and the definition of the parser struct specifies that the lifetime of the reference to context and the lifetime of the string slice that context holds should be the same. The problem is that the parse context function returns the value returned from parse. The lifetime of the return value of parse context is tied to the lifetime of the parser as well, but the parser instance created in a parse context function won't live past the end of the function, temporary, and context will go out of scope at the end of the function. Parse context takes ownership of it. This is getting a little bit difficult to read because like the constant repeating of parse context and parse. Rust thinks we're trying to return a reference to a value that goes out of scope at the end of the function because we annotated all the lifetimes with the same lifetime parameter. The annotations told Rust the lifetime of the string slice that context holds is the same as that of the lifetime of the references to context that parser holds. The parse context function cannot see that within the parse function, the string slice returned will outlive context in parser, and that reference parse context refers to the string slice, not context or parser. By knowing that what the implementation of parse does, we know that the only reason the return value of parse is tied to the parser instance is that it's referencing a parser instance's context. which is referencing the string slices. So it's really the lifetime of the string slice that parsecontext needs to care about. We need a way to tell Rust that the string slice and context and the reference to the context and parser have different lifetimes, and that the return value of the parsecontext is tied to the lifetime of the string slice and context. First, we'll try giving parser and context different lifetime parameters, as shown in listing 1915. We'll use lifetime S and C as lifetime parameter names to clarify which lifetime goes to the string slice, context, and which goes to the reference to context and parser. Note that this solution won't completely fix the problem, but it's a start. We'll look at why this fix is not sufficient when we try to compile. So struct context. So now we're using S as our lifetime to denote that this is a string. So this is the one that we want to match in parse context. So struct parser, we have C and S, context. So lifetime of C context, we're using context of S, implement lifetime of C, lifetime of S, parser, lifetime of C, lifetime of S, function parse self, returns a result that does nothing, or returns a reference to lifetime of S of string or stir, returns an error, so the reference to self to context. Okay, so nothing changed there. Then we have our function parsecontext. This one doesn't need lifetimes then, or maybe it does, and they're not showing it yet. We've annotated the lifetimes of the references in all the same places that we annotated them in listing 1913. But this time, we use different parameters depending upon whether the reference goes with the string slice or with the context. We've also added an annotation to the string slice part of the return value of parse to indicate that it goes with the lifetime of the string slice and context. When we try to compile now, we get the following error. So error in type reference lifetime C, context lifetime S. Reference has a longer lifetime than the data it something. Okay. The pointer is valid for the lifetime C as defined on the struct, but the reference data is only valid for the lifetime S as defined on the struct. Rust doesn't know of any relationship between C and S. To be valid, the reference data in context with lifetime S needs to be constrained to guarantee it lives longer than a reference with lifetime C. If lifetime of S is not longer than lifetime of C, the reference to context might not be valid. Now we get to the point of this section. The Rust feature lifetime subtyping specifies that one lifetime parameter lives at least as long as another one. In the angle brackets where we declare lifetime parameters, we can declare a lifetime A as usual and declare a lifetime B that lives at least as long as A by declaring B using the syntax B : lifetime of A. So we actually did this before, way back in the old days when I wanted to give everything different lifetimes. When you had two things coming in, and one of them was going out. One of the references was going out, and so I say like, okay, well, coming in lifetime A, lifetime B, but the B lifetime was the same as A, and I thought that's what I meant, was that it's essentially just like typing, right? It's the same lifetime, but it's basically saying. It's okay, so it is typing, it's subtyping. We're saying the type of B is the same as A. In our definition of parser, to say that lifetime of S, the lifetime of the string slice is guaranteed to live at least as long as lifetime of C, the lifetime of the reference to context, we change the lifetime declarations to look like this. So struct parser, lifetime of C, lifetime of S, which subtypes C. Now the reference to context in a parser and the reference to the string slice in a context have different lifetimes. We've ensured that the lifetime of the string slice is longer than the reference to the context. That was a very long-winded example, but as we mentioned at the start of this chapter, Rust's advanced features are very specific. You won't often need the syntax we describe in this example, but in such situations, you'll know how to refer to something and give it the necessary lifetime. Lifetime bounds on references to generic types. In the trait bound section in chapter 10, we discussed using trait bounds on generic types. We can also add lifetime parameters as constraints on generic types. These are called lifetime bounds. Lifetime bounds help Rust verify that references and generic types won't outlive the data they're referencing. As an example, consider a type that is a wrapper over references. Recall that ref_cell_t type from the ref_cell_t and the interior mutability pattern section in chapter 15, its borrow and borrow mute methods return the types ref and ref_mute, respectively. These types are wrappers over references that keep track of the borrowing rules at runtime. The definition of the ref struct is shown in listing 1916 without lifetime bounds for now. That's a lot of important information crammed in that little turbofish. I could see easily missing that reading someone else's source code. I know it does seem to be that, and I kind of wonder whether or not it would be better to move on from single letters to words at that point in time. I vaguely remember that we can use however long we want, and it's just been convention to use single letters because everybody else does it. But maybe, I mean, as long as we stay away from static, every normal variable would be available to us, right? So struct ref, lifetime of A, and then generic type, reference, lifetime of A, okay. Without explicitly constraining the lifetime A in relation to the generic parameter T, Rust will error because it doesn't know how long the generic type T will live. So we're gonna have to do like lifetime of A colon T or T colon lifetime A. Because T can be any type, T could be a reference or a type that holds one or more references, each of which could have their own lifetimes. Rust can't be sure T will live as long as A. Fortunately, the error provides helpful advice on how to specify the lifetime bound in this case. Consider adding an explicit lifetime bound T, yeah, so exactly, T colon lifetime of A. So the reference type does not outlive the data it points to. Listing 1917 shows how to apply this advice by specifying the lifetime bound when we declare the generic type T. So yeah, exactly this. Declare lifetime of A, but also make sure that T has at least lifetime of A. I mean, this is all like sort of getting into like crazy, really cool stuff that can be done, but also I could see, yeah, I could agree that it might be really hard to see unless we're looking for it. This code now compiles because T colon A syntax specifies that T can be any type, but if it contains any references, the references must live as long as lifetime of A. We can solve this problem in a different way, as shown in the definition of a static ref struct in listing 1918 by adding the static lifetime bound on T. This means if T contains any references, they must have the static lifetime. Okay, so we're just adding static to the generic T. Because static lifetime means the reference must live as long as the entire program, a type that contains no references meets the criteria of all references living as long as the entire program, because there are no references. For the borrow checker concerned about references living long enough, there is no real distinction between a type that has no references and a type that has references that live forever. Both are the same for determining whether or not a reference has a shorter lifetime than what it refers to. So then why would we need that? Inference of trait object lifetimes. In chapter 10, in using trait objects that allow for values of different types section, we discussed trait objects, consisting of trait behind a reference, that allow us to use dynamic dispatch. We haven't yet discussed what happens if the type implementing the trait in the trait object has a lifetime of its own. Consider listing 1919, where we have a trait red and a struct ball. The ball struct holds a reference and thus has a lifetime parameter and also implements trait red. We want to use an instance of ball as the trait object. So box dying red. So you have trait red, which is an empty struct ball, which is a lifetime of A. It has diameter of the reference lifetime of A of I32. We implement lifetime of A, red, for ball, and then that's okay. So it's an empty trait here, so we're just implementing that. For ball, lifetime of A, and that's empty because there's no function definitions set on it. Function main, let num is 5, let object equals box new. So we're putting the ball into a box. Ball diameter is a reference to the number as, so then we're casting it into a box, which is a dyne red. Interesting. This code compiles without any errors, even though we haven't explicitly annotated the lifetimes involved in obj. This code works because there are rules for working with lifetimes in trait objects. The default lifetime of a trait object is static, with reference to lifetime of A, trait, or reference to lifetime of A, mute trait. The default lifetime of the trait object is lifetime A. Okay, with a single T, so generic type with lifetime of A clause, the default lifetime of the trait object is the lifetime of A. With multiple clauses like T lifetime of A, there is no default lifetime, must be explicit. When we must be explicit, we can add a lifetime bound on a trait object like box dyne red using the syntax box dyne red plus and then the static lifetime. Interesting. Or box dyne red plus lifetime of A, depending on whether the reference lives for the entire program or not. As with the other bounds, the syntax adding a lifetime bound means that any implementor of the red trait that has references inside the type must have the same lifetime specified on a trait object bounds as those references. Next, let's look at some other advanced features that manage traits. So, I mean, what I'm getting for this is like, this is the type of stuff that I would need to worry about if I'm creating libraries that other developers are going to be using. And I think I'm going to begin with Rust not by creating libraries that people are going to be using, but programs that are utilizing other people's libraries. And I think that's the reason why this is more in the advanced section, is I'm not going to need to worry about this yet at the beginning of like actually building real life code. But eventually, if I like bring Rust into my workplace, we are going to be creating libraries that the other developers and the teams would be utilizing, and therefore this would suddenly become important. Which probably all, like as I just get more comfortable and familiar with Rust, and my understanding about how it's working like just grows, this will become more apparent to me. That's kind of what I'm hoping. Is your workplace willing to bring in Rust? Probably not. Right now I'm working at well, it's interesting. I'm working at Galvanize, which is a code school, and we do have a software engineering department, but I am actually an instructor there. So I'm not part of those teams. Their stack, like the Twitch thing just application just opened in front of my stream window, and I don't really care for that. They're using a Ruby on Rails application for the most part. I have thought about like teaching some basic Rust stuff there and like getting students going with that, but they're also like learning to code from scratch. Like they can definitely do that. I think I want to go through this first before I might like suggest that anybody uses Rocket or something else to create one. But I've had a student use Scala before, and that's a very functional like language that they used as a backend to create a kind of RESTful API. So I don't see a reason why a student wouldn't be able to like use that. I just don't think we're gonna teach it fully. I think we're gonna let students, experiment with it on their own, and I'll just reference these videos and say like, great, you have 1.5 weeks to learn how to do something, and here's like 60 plus hours of videos for you to learn in that 1.5 weeks. Good luck. Also, you need to build the project, so it's not just learning time. It is 7:51 and my throat's starting to feel a little bit scratchy right now. A ton of talking after not talking too much. So what I think I'm going to do, the long section, I think I'm going to just sort of save this and set this up for next time. Let's come and reset ourselves. So we have playing with unsafe Rust. Unnamed outsider. Really impressed you kept this up, man. Thank you very much. It's actually like, I don't think I would have made it through this book if I wasn't doing streaming. Mainly because like I've noticed that I sort of get bored going through stuff, and I just want to then like just do. And in the side, I've been like playing with random little things here and there, and doing this stream has helped me like stay on it, and I think it is good. It helps me learn a little bit more, and I'm looking forward to finishing this and then on stream building some things. The good news is it would be good teaching students that once you know the fundamentals of programming, you can pick up any language in a short amount of time. That's definitely true. We had a 100 cohort celebration last night, and the number of students that came up and go like, yeah, I'm working with Go now, or I'm working with Java, or Python, or any number of other languages. And I had no idea that like the real world was going to be like this crazy, and just jumping from like, one person said that they're jumping from like 3 languages every single day because that's the stack that they're on, and they're one of the only developers in the company, and they're just building the stuff, and that was really awesome to hear. But let's go ahead and updated that. You then. And then we'll update. We'll update where we're currently at, which is advanced traits. Okay, now the spider is moving towards me. Hold on 1 second, I've got to deal with it. And done. I would have been more happy if it just stayed in the closet and not ran towards me. All right, so where was I? Okay, so I did update traits. Now we got to do the URL. All right. That's where we're at. We'll update this. Updated where we are at. And let's go ahead and send this on up to GitHub. I shouldn't need you to tell me that every single time over and over and over again. All right, so I've updated GitHub. I'm gonna go ahead and share this URL that everybody can see it. All right, so I have this linked in the stream description too, but I'm also putting it into the chat in case anybody, and in case for some reason you're able to find those, you can just sort of read this URL here. Basically, I have all of the code that we've been working on through this entire book. We're currently in chapter 19 that we've been writing through here. We also have a wiki that when we've been doing projects and we have to look something up on Google, we've been throwing that information into the wiki. The wiki is also updatable by any of us, so I'm hoping that this will be a community wiki for learning Rust. And then I'm also archiving these videos over onto YouTube. So I have an entire playlist of every single video from chapter 1 all the way through here, partway through chapter 19, and there's nothing going to stop me. So I'm going to continue on next week and making more of these videos. We're going to get through chapter 19, and then we have this really awesome sounding project creating the multi-threaded web server, which doesn't sound like it's going to use any of the frameworks for creating web servers. So that's actually going to be really interesting to sort of see what those frameworks are doing behind the scenes. So that way when I use something like Rocket or what's the other one? I just had it the other day because I went to the Rust meetup and they were chatting about it. But it's like Alta something. I forget. Altex Web. Yes, that's what it is. And so I might play around with all of those things. Actix Web. Yes, it's you're correct, Stacking. That's what it is. So I'll probably do projects where I'm going to create different web servers and all of them, and just sort of see which ones I like the most. And then we'll just move on from there. So if you've been enjoying these streams and these videos, please follow me on Twitch here so that you can get notifications of when I go live. You could also follow me on YouTube in the case that the algorithm is nice and lets you actually see when I've been updating those. I do have a Twitter account, and I've set up YouTube to automatically tweet whenever I archive one of the videos and put them into the playlist. So that way at the very least, if you're following me on Twitter, you can see when I'm going to go live and when I'm actually have archived a video. One is sync, the other is async. Oh, interesting. Well, we'll also play around with that. We haven't the book hasn't really talked about async code at all, and I think that's a future something, or is that something in 2018 that's now available? I don't actually remember. Yeah. Anyways, I've been doing this stream every single weekday morning at 7 a.m. Mountain Time, and I'm going to continue that next week. And if for some reason I'm unable to make a stream, I also tweet that out. So with that, I'm going to go get ready for the rest of my day. It's a nice sort of Aloha Friday, so I'm wearing my my Hawaiian shirt, and then we'll have a great weekend, and then continue on next week. 2018 roadmap is pushed back until 1.29 to 1.31, and futures aren't part of it. Oh, okay, that's too bad. Well, then we'll see it next year, I guess. But again, with that, I hope that you all have a great rest of your day, and I'll see you next week, Monday at 7 a.m. Mountain Time. And click.